Hello everyone and welcome back to the channel. Today I am hoping that this video is not going to be too long because I have around 6 quest bars swimming around in my stomach at the moment, and soon we will be in for somewhat of a volcanic eruption. So I'm guessing that's going to be probably within the next 20 to 30 minutes, so that's how long I'm going to try to take. Anyways, today we're going to be learning about Presto. Okay, so today we are going to be talking about Presto. So basically, Presto is a paper that came out only a few years ago. It looks like 6 now, out of Facebook, and since then it's been open sourced and rebranded to something known as Trino. So if you hear either of those terms, we're kind of talking about the same thing. Presto, I guess, is an older version, and then now they're developing it under the Trino name. Basically, the idea here is that we've got all of these different object stores, we've got all these different data warehouses, we've got all these different databases, all of which we want to query, right? And we all want to query them through the same interface, which is effectively just SQL. So what we want to be able to do is use one unified compute layer to run queries on all of these systems. Now, in theory, you don't necessarily need that compute layer if you're only querying a database, but when you start bringing things like object stores and data warehouses into the mix, maybe you do need this extra computing power. So basically, to add an additional data source into something that Presto can query, because not everyone has the same dialect of SQL, you need to basically just implement something called the connector API, and then all of a sudden you can read into Presto, so read data in, do joins on it with other data sources, and then write back out of Presto into an external data store. So this is multi-tenant, right? Everyone at Facebook is using a shared cluster, and then also it's trying to aim for as high a throughput as possible with some nuances where basically if you have something like an interactive query, right? So if I'm a data scientist and I'm running all these queries and I want them to return as fast as possible because I need it for my day-to-day workload, it's important that those finish really quickly, and it's less important that things like massive ETL jobs, which are less latency sensitive, are finishing super fast, but they're just more so it's important that they're getting a lot of throughput. Cool, so let's go ahead and go through the architecture of this Presto system. Basically, like many of the other systems that we've seen in these papers, it just uses a single coordinator. This makes life a lot easier when it comes to planning work on a bunch of executors. So the coordinator is going to basically take in a SQL query, it's going to admit it, and decide whether to accept it or reject it. It's going to parse it into some sort of logical query tree. It's going to perform planning and optimization, where you basically take the tree and figure out what statements are necessary or unnecessary and optimize that a little bit. We'll talk about that in a bit. And then you've got all of these Trino workers or Presto workers over here. And so basically the idea here now is that the coordinator is scheduling a bunch of tasks onto these workers, and then once all of these workers have tasks scheduled on them, maybe they have to read from some sort of external storage system, right? So they're going to go to the storage system, say, hey, I'm supposed to read from you, and the storage system is going to assign them a bunch of splits, where splits is basically just pieces of data that they have to read from the external storage system. Once they do that, they can start performing all of their tasks. Obviously, the workers are also going to be communicating with one another when it comes to doing things like shuffles, and they also have to communicate with storage to read from it in the first place. Okay, so the first thing that we're going to be talking about here is the logical plan in Presto. So basically, to describe what a logical plan is in a SQL statement, all it really is basically it is a bunch of operators that are grouped together, and the idea here is that there's no actual information on how they're executed, right? It's more so just something like scan this data set, filter it based on this condition, aggregate it based on this other condition. And so, when we're querying from Presto, we want to basically make this plan as efficient as possible, and there's a few things that we can do so. One is just called predicate pushdown, right? So if you have any filters, you want to apply those as early on as possible. And for certain systems, you can even actually apply them even earlier than that, such that it's not even in Presto, right? So if Presto is scanning MySQL, and then you have some filter that specifically applies to that MySQL dataset, you also want to run that filter when you're querying from MySQL, because that limits the amount of data that's coming back to you over the network. So you can do it for something like MySQL. For something like Hive tables or iceberg tables or anything like that, where it's a bunch of Parquet files in object store, you can't necessarily do filtering because you don't actually have CPUs that are running queries there. What you can do potentially is do some amount of file pruning based on min-max filters, min-max headers and Bloom filters and things like that. There's also column pruning, so this is just an optimization that most databases are going to run, where it's like if you're fetching a column from one data set, but then you don't actually return it in your result output, then don't actually fetch that column. And this works nicely because this is mostly going to be column-oriented storage. And so, omitting fetching an additional column is going to save you a lot in terms of performance. Finally, we've got this other thing called decorrelation, which was a new term to me, but it does make a lot of sense. So if we have some query like this, where it's like select a field from one table, select another field from that table, and then select this other field from a second table, where we're basically running a query every single time on every single row of our output, we can basically just go ahead and optimize that and perform a join instead. So we're joining our tables E and D over here using this ID field that they have in common. And as a result, this now becomes O of n as opposed to O of n squared, where this particular piece of the query is being run once per row. So that's just a logical optimization, right? The query plan is changing. And then now what we move into is the physical plan. So the physical plan is taking the logical plan. It looks very similar, but for certain things like joins, for example, it's actually describing how we're going to be running that query. So this could be things like join strategy selection, right? So maybe we're using a hash join where one side is building a hash map and the other side is probing it, looping through it to basically figure out all the records that match. You can do a sort merge join if two data sets are joined in the same way, or also partitioned or co-located joins, which is basically when two data sets are also partitioned or spread out over a bunch of different nodes in the same way, and so that way you don't have to do an additional shuffle phase. There's also join reordering, right? So if I'm joining three data sets, you basically want to be sure to join them in some sort of order where the intermediate state of joining the first two doesn't balloon out to a huge size and then get very small again. So ideally, when you're joining three data sets, you want to be joining them in an order such that basically any state that you have to maintain after joining the first two data sets is as small as possible. So basically the way that Presto is doing physical plans is they're using a bunch of cost estimates. This is very standard across databases, and it's more so how you're creating the cost estimates that's going to be the tough part. In their case, they're using a bunch of column statistics and also table level statistics. So, things like number of rows, maybe the min-max in a column, looking at partitions as well. And also, when it comes to making things like join strategy decisions or join ordering decisions, it also really helps to account for actual physical layouts of the table, of which there can be many, right? So for a given table, it can be sorted in many ways. It can be partitioned in multiple ways. It can be grouped in multiple ways. It could have different indexes. And the idea here is that the cost optimizer is aware of all of these things and can be intelligent about which physical layout it's going to choose for a table to execute an operation most efficiently. Okay, now we're going to talk about a couple of terms that are specific to Presto, though I have seen them used in other database papers. But the idea here is that when we have a query, we break it down into multiple different stages, right? So the stage is basically the unit of operation. They have this similar concept of stages in Spark, and the main idea is that each stage is separated by a shuffle phase, meaning that you have to finish the prior stage completely so that you can do the shuffle and begin the next stage. Now, it's worth noting that we don't really want to be doing a lot of shuffles, right? Because shuffles are super expensive. You're taking a bunch of data and you're sending it pretty much from every node that's executing a query to all of the same nodes executing the same query, but you're also, doing a bunch of sorting, you're using a bunch of CPU, you have to have all of this data stored in memory temporarily in these input and output buffers. And so we don't really want to be doing this. In fact, we want to be doing it as infrequently as possible. So basically the way that Presto decides when it's going to shuffle or when it's not is every single operator. So every single operator where an operator is something like a filter or a hash join or a scan or a projection from one field to a different value on it. Basically, all of these things are going to have this concept of a required property and preferred properties. So that's basically describing how they would like the input data that they're taking in to look in terms of how it's partitioned, how it's sorted, things like that, to make it as efficient as possible. Now, certain things are going to have required properties where they need to be partitioned in a certain way. So for example, if you're doing a hash join, you need basically the same partitions of both data sets to be on the same node. And in that type of case, then now all of a sudden you have to shuffle. So basically the way we decide when we want to shuffle in Presto is we greedily assign shuffles. So we're going to basically look at all of the required properties of all the operators, and we're only going to shuffle when we have to satisfy those required properties. So within a stage, each stage is broken into multiple tasks, where you can think of a stage, again, as some great computation, but then that computation has to be distributed across multiple workers. So each piece of the stage is called a task, and a task is delivered to one of many workers. So basically a bunch of workers are running tasks at the same time. So these are just going to be a bunch of pipelined operators. So for example, a task could be, scan a data set, then filter it a bit, then do some projection on it and add one to this certain field. So those are going to be given to a worker node. Those are being scheduled. And if possible, or if useful, tasks may be multi-threaded, right? So if you're doing a lot of work, you want to multi-thread on that single worker because you're going to get better parallelism. Okay, so now we're going to talk about stage scheduling a little bit. Like I mentioned, we've got all these unique stages where, for example, if this is a hash join, and we've got a bunch of nodes, right, over here and over here, stage one is everyone gets data in, then they have to go and shuffle, and then after that you can finally perform the hash join. So I guess there are two ways of actually scheduling all of this computation. Number one is called the all at once mode. So basically every single task is scheduled right at the start. We're going to do work as soon as there's data available to be done, and that's totally fine. That is going to result in lower latency queries. At the same time, when you're doing a bunch of tasks at once, there's inherently going to be overhead for that. You have to keep track of state for those tasks. You have to keep track of intermediate memory. And so that is going to be good for interactive queries, but you probably don't want to do it for something like an ETL job. On the contrary, you've also got this concept of phased operators, right? Where basically we understand that there are dependencies between stages in a SQL query, and as a result of that, you can basically wait for all of the upstream operators to completely finish before you run downstream ones. This is going to be a little bit less intensive on the entire compute cluster, and as a result, it's better for things where we don't care about the latency as much. Okay, next let's go ahead and talk about picking nodes for our task scheduling. So in Presto and Trino, there's this concept of splits, where splits are basically going to be only relevant for something known as leaf tasks, where leaf tasks are the ones that read from external storage systems, whether that's MySQL or HDFS or S3 or anything like that. So when you're actually having a leaf node to read this external storage system, the storage system is going to go ahead and basically say, okay, here are a bunch of pieces of data that I want you to read, and those are going to be the splits. So for these leaf tasks in particular, we want to be as efficient as possible considering our network topology. So for example, if we're reading from Hadoop, it gives us the option to basically go ahead and perform the task of the leaf task itself on the node where the data lives, so we can get better data locality. That being said, if we're using something like S3 where you literally can't run the task where the data lives, then you'll just run on any node in the cluster and it's not a big deal. For intermediate tasks, which is pretty much every other task in the query other than a leaf task, you can basically run this guy anywhere, and we're pretty much going to try and schedule that task split up onto as many nodes in the cluster as possible, within limitations of one node being like, hey, I'm overloaded. So basically, in terms of deciding the number of tasks per stage, that's done based off a bunch of heuristics, which Trino doesn't get too into in the paper. But the idea is, you want to distribute this work as much as possible over the nodes in all the clusters. Okay, one nice thing that they do, which is a cool feature that they touch upon, is called lazy split assignment. So like I mentioned, when you go to a storage system and say, hey, I have this task to read from you, the storage system is going to come back and say, okay, well, here are all these mini splits that you can read from, which is all the data that you're interested in. So it's going to split it into many different parts. So basically, the idea is to do this type of thing lazily, right? So what lazily really means is that, when you go to a storage system like Hadoop and you say, hey, tell me all the things that I have to read, it's going to start telling you the things that you have to read, but it's going to tell you, one at a time, right? So that means if you've got a couple of different workers over here, where one of them is particularly slow and one of them is particularly fast, you basically always assign the newly calculated split to the one with a smaller queue. So that means if I have a fast worker that's really running through these splits very quickly, and then this guy is a slow worker, I'm assigning more tasks to the fast worker over time, which is very, very nice. This is good for a couple of reasons. For one, part of the reason Iceberg exists in the first place is because before that, everyone was using this Hive table format on S3 or Hadoop or anything like that, and that can take a really, really long time to figure out all the splits because you have to do like an ls on your directories in Hadoop, which takes a while. Another thing is that you don't need to hold all of these in memory. By the time I'm getting more splits, maybe my fast worker has already processed a bunch of them, and so now I can just garbage collect that memory and get it back. So yeah, again, better load balancing, better memory efficiency, and yeah, it just takes a while to get all these splits, so it makes a lot of sense. Okay, in terms of actually scheduling all of these tasks on the workers, keep in mind that this entire architecture is multi-tenant, right? So if I'm a data scientist, I'm running on the same compute nodes as data engineers that are running these massive ETL jobs, which are going to be super compute intensive. And so we have to be able to balance the workload between all of these things and make it fair. So the way that they do that is use something called a multi-level feedback queue. So this might be something that you vaguely remember from your operating systems class. I kind of do. But the gist is, if I'm a CPU, you can have basically a bunch of tiers of tasks, right? So maybe in the lowest tier, you're saying, okay, 50% of my cycles are going to go to all of the tasks in the lowest tier of this feedback queue, 30% to the next one, 15%, and then 5%. And so basically, as one task keeps taking longer and longer to run, right? So we'll basically take a task right here because it's at the beginning of the 50% queue. It's going to run for a second, and then it's going to give up, okay? So it's going to do that a few different times, and if it's still running because, maybe it's a big ETL job and this takes a while for this to run, then it gets demoted to a higher level of the multi-level feedback queue. So actually, in this case, it would go all the way over here, and as a result of that, now it's running in the 30% tier. So it's actually going to start to take longer and longer to run this thing, the longer that it runs on the whole. And the effect of that, basically, is that queries that should be going fast because, they're just not reading that much data. So, for example, like data scientist queries or, queries that are ingestible by like an actual human as opposed to a massive system are going to be prioritized quite a bit more. That being said, it's going to keep the actual CPU usage of the cluster extremely high because it means that, if for whatever reason there is nothing in this queue right here, it's just going to be running the other stuff. So you're going to get a lot of throughput. Basically, every single task is going to just run for a second at a time, and then we're going to reevaluate which level of the feedback queue it goes back into after it yields. The one problem with a system like this, or I guess two problems that they mentioned in the paper, is number one, you may have this concept of uneven splits, right? So within a leaf task, you can have multiple splits. And so one leaf task may kind of get a bad rep if there's one particularly large split that you're reading. That being said, the remainder of the splits in the leaf task are, fairly easy to read. You still may end up finding yourself all the way up here. Synchronous APIs are also a problem. The reason being, if you're connected to, this external storage system and you're reading data from it, and there's never a place where you're able to like yield and then come back and get that data, then now all of a sudden you could be running for minutes at a time, pulling data from the system, and every other task is getting starved and is not able to run. If that does happen, the system is still accounting for how much time that synchronous API called, or how much time that synchronous API was, and it's going to put you probably right all the way up here in that 5% task. Okay, the next thing that they talk about quite a bit in the paper is what's known as shuffle buffers. So recall, when we are shuffling from one node in the system to other nodes in the system, what that really just means is we're taking data and we're sending it over the network. In the case of Presto, they're just using HTTP long polling to do so. The reason they're using long polling over the occasional just like normal poll is they want to minimize latency as much as possible. And another thing that they're doing is basically saying, okay, in order to ensure that we're not garbage collecting data in a buffer too early before it's sent over as part of the shuffle, we're only going to drop old data when the next poll comes in. So if we look at the diagram over here, let's say this guy is a scan over here, and then this guy is like a hash join. So you have to do a shuffle in between those. The scan is going to have some amount of output buffers, right? Because you take the data, you buffer it in some array, and then all of a sudden you're now waiting for the hash join operator to request it from you so that you can shuffle it over there. So you do that multiple different times because you're sending data in batches. And so, on request one, maybe we get this batch from the output buffers. And then, now we've got some more output data over here. So request two comes in with some, token saying, hey, this is the one after request one. And then the scan operator can say, oh, I see that this data has already been used before, or I no longer need this data. Let me go ahead and garbage collect it. So when it comes to these shuffle buffers, there's actually a lot of tuning that needs to be done for a few different reasons. So I'm going to try and go through them right now. So if our output buffers are too small, basically what this means is we're going to block our upstream operator, right? So if this is a scan operator and our output buffer is full, we can't really do any scanning from the external file system because all of a sudden we have no memory to write that data into. Similarly, if our input buffers are too empty, now all of a sudden we have a ton of overhead, right? So we're processing all of these input buffers, in our actual hash join operator, and if we're only processing a little bit of data at a time, we're not going to be able to take full advantage of things like vectorization and parallelization, and we're just going to be wasting a lot of CPU cycles, which is not good either. On the contrary, if we're letting our input buffers get too full, kind of the same idea, we're going to be blocking upstream operations because then we're not going to have any new room to take in our output data over here. So again, it's all about tuning, and this is going to be a problem as well. One reason that you may end up seeing your output buffers of a shuffle phase be too full is because the quote-unquote downstream operator, or the consumer of that data, is particularly slow. So this may happen with slow clients. So if I'm a data scientist and for whatever reason my internet's really shitty and I'm pulling from Trino, you may literally see output buffers getting filled up. And so what they do in order to optimize for this case is if they find that output buffers are always being too full for a particular query, they'll actually just lower the number of the concurrent scan tasks that are actually going to the external file system so that you're not pulling in as much data and you don't have to worry about overflooding those output buffers. This is also good because it just allows other scan tasks to run at the same time and doesn't overload your network bandwidth, which is very nice. Another thing that they also do is, depending on how full those input buffers are for something like a hash join operator over here, they're going to basically tune how many long polls that operator is making at the same time, or how many concurrent long polls they're doing at the same time, to either fill them up a little bit more or make them a bit less full. At the end of the day, they also do something similar with writes to external file systems, right? So when you're about to write to something like Hadoop or about to write to something like S3, again, that data is being placed in an external buffer so that you can basically chunk it and get batch writes and get more efficient overhead. Now, that being said, if you're allowing your external buffer to barely be filled and then making a bunch of writes at the same time from a variety of different threads, now all of a sudden you have a bunch of small files. Now, having a bunch of small files in something like S3 or Hadoop is problematic because when you want to read them back, now you basically have to check the metadata for every single small file, which is going to take a really long time. Maybe in theory you can prune a lot of them out because now you have more granular metadata statistics, but typically it's considered to be a much better thing if you have quite a few bigger files as opposed to smaller ones. So basically what we do here is we use a couple of heuristics to basically tune the level of concurrency with which we write to external file systems so that we aren't creating too many small files at a time while also not creating files at too slow of a rate. Another thing that is fairly useful in Presto/Trino is how they handle query memory, right? Because you don't want a bunch of your executor nodes running out of memory all the time. So they define two terms in the paper. Number one is going to be user memory. So a bit of an oxymoron. User memory is basically how much your memory your query, or how much of your memory that your query is using because of the actual query itself, right? So if I say, select star from some massive table, that's going to have a ton of user memory. At the same time, there's also this concept of system memory, where system memory is completely unrelated to the actual query that you're running itself, and is more so related to things that are tuned about Presto or Trino, like the actual shuffle buffer sizes or the write buffer sizes that we discussed in the last two slides. So basically in this system or in this paper, they impose limits both on the user memory and also the user plus system memory per query, which I think they call the total memory, but I can't recall off the top of my head. So basically, what they may end up doing is they're very much willing to kill tasks that are exceeding these limits, both on the entire cluster and also a single node. That being said, it's possible that you're just running so many tasks at once that we physically run out of memory in our cluster, and that would be a problem. So what do we actually do when that happens? None of them is necessarily violating their individual memory limitations, but we've just got too many queries running at once. Well, in this case, they have something that they call the reserved pool, where the reserved pool basically it runs, there's one reserved pool for the entire cluster, and one query can be in it at the same time across all workers in that cluster. So basically, the highest one, or the one that takes up the most memory, goes into the reserve pool. It is allowed to complete, and then ideally everything else can continue. They prefer to do something like this in practice as opposed to something like spilling to disk, where you take kind of like your intermediate hash join state, so like your build phase of it, and put that on disk, or your hash map that you use for aggregations and serialize that to disk, because that just really makes performance hard to reason about and much more inconsistent. So they much prefer using this reserved pool, or if anything, they'll just kill a few queries instead. It's also worth noting that on a per node basis, the memory limits are higher proportionally than they are across the entire cluster. The reason being that you see skew in terms of the amount of memory that's needed per task across all of the nodes in the cluster. So for example, if these are two splits right here, one of them may have much more data in it than the other, just completely randomly, and as a result of that, we don't want to make the per node memory too low, because there can just be variance across the splits of how much memory is needed. They do a few different garbage collection optimizations in the paper as well. So ultimately, this is a system that is built on top of Java, and as a result, that is a garbage collected language. Now they use one that is called G1 in particular, which I'm not going to go into too much, mainly just because I don't know that much about it. But as far as the paper is concerned, basically they say, number one, G1 is pretty poor at handling really, really large objects. And so if they have like this massive array that they want to keep, they'll actually split it into multiple different pieces to try and improve how G1 handles it. At the same time, even though it's really helpful when you have massive objects to split them up, if possible, they also try and avoid having a ton of really, really small objects, because, if you're doing garbage collection, you have to keep track of which objects reference other objects so that you can get rid of an object when it's no longer necessary to keep around. That being said, keeping track of all these pointers is really expensive, so if they can reuse objects for multiple different things, they choose to do so. The example they gave in the paper was that for like the histogram object, they try and reuse that one like across different queries or different tasks in order to limit the number of objects they have for it. Another thing that they do in Trino/Presto is code generation. So this is in contrary to some of the papers that we read, like Databricks Photon, where they explicitly say, screw code generation, we're going to use vectorized processing with a bunch of primitives in C++. So this instead is you write everything in Java. That being said, for certain parts of the code, you're actually going to generate custom Java bytecode that is more amenable to the JIT compiler. So let's try and break that down. Basically, when you're running a language like Java, first your code that you write gets compiled to something known as Java bytecode. Then Java bytecode is read one line at a time and interpreted. And then you also have this thing called the JIT compiler, the just-in-time compiler, where the JIT is looking at certain areas of that Java bytecode that it can kind of run a little bit better and perform optimizations on, and it will do so if possible. That being said, they note that there are certain areas in their code where the JIT is not doing exactly what they want it to, and so this is where code generation comes really handy for them, because they can generate bytecode that is more amenable to that optimization. So one example is the fact that, if you recall, every single operator on a worker node is running for 1 second at a time and then completely yielding, and then something else is going to run. And they do that so that they can balance out the fairness of all these queries. That being said, if something's just running for a second at a time, it's really hard for the JIT to profile that method well and get a sense of whether it's taking a while and what parts of it are taking a while and all of that. And so instead, they're writing custom bytecode to basically help the JIT understand which pieces of those operators are going to take a long time and should be optimized. Another thing that they're doing is actually creating bytecode for operators for every single type. This is because, if you recall, we discussed this one, I think maybe also in the Databricks Photon paper, but the main idea is that, when you have virtual method calls, so virtual methods happen a lot when you have things like, wildcards and subtypes and anything like that. The reason it's problematic is because you don't know at compile time which version of the method is being called. You only figure that out at runtime. And so, a compiler can't really do any extra optimizations there. That being said, if you generate all of these classes and you do so basically one per task at compile time when you create your bytecode, then all of a sudden the JIT can actually look at that generated class, and it also knows at bytecode compile time the actual type that you're running on, because of the fact that the SQL engine knows what type you're running on. So when I say, select X from some table, the SQL engine knows what column X is, and so it's going to compile bytecode that basically has X hard-coded as, say, an integer, for example, or a string, but not a situation where it can be both of them. So once we actually know what type certain things are, we can get rid of those virtual function calls. We can go into our loops and we can do something called unrolling them, where instead of having all of these branches to check if your loop condition is satisfied or not, you basically just hard code like a bunch of different iterations of a loop, and you get a bunch of other performance benefits out of doing all of this. So I think mostly that is going to describe it, but basically, having all of these different classes and doing all this code generation can yield a lot of performance benefits when dealing with the JVM. This is not easy to do. It is certainly not trivial, and I don't know that I will be attempting it myself anytime soon, but it is something that they do nonetheless. Okay, finally we're going to talk about actually operating on the data within Trino or Presto. So basically, they're going to be attempting to operate on data in columnar formats, and so this data is coming in pages is the term they use. So think of that almost like a Parquet file where you've got all these row groups. So you've got, maybe let's say 100 rows or 1,000 rows, but they're encoded in a columnar format. So all the column values for the same columns are stored together within that row group. So you've got multiple rows there, and then per column we call that a block. So again, we do plenty of data skipping when possible, which is basically, we have this metadata per column, with things like min-max headers and also Bloom filters, which is going to allow us to skip as much data as possible and process, fewer rows. Similarly, we are going to be doing things like dictionary and run length encoding, which I'll demonstrate in a second. But the idea there is that you can actually operate on dictionary and run length encoded data directly, as opposed to having to first decompress it and then operate on it. So what would be an example of a dictionary? Well, let's say we have this table right here where we've got a name field and who they have a crush on. Note how in this who you have a crush on category, Megan likes Jordan, Kate likes Jordan, Corinna likes Jordan, and Sydney Sweeney also likes Jordan. So if we need a dictionary to represent that column, it only has to have one value. And if it only has one value, that means we only need one bit to represent the entire column, which is really great. That's going to save us a lot of space. Now note that for run length encoding, again, we have a bunch of repeated values. So we've got 1 4 times in a row. So that can actually be encoded even faster by basically using a bit for 1 over here and then a couple of bits for 4 over here to basically say, hey, this one entry is happening 4 times in a row. Now, how do we operate on those directly? Pretty simple. The main idea is, let's say you have some massive column, which is dictionary encoded, but the dictionary itself is very small relative to the number of rows in the column. All you have to do is just, call the function on every single item in the dictionary. So maybe you've got an 100 element column, but there's only 4 dictionary values. This is very prevalent when dealing with something like enums. You just compute the value for every single enum, and then now all of a sudden you don't have to compute that value 100 different times. If we're dealing with run length encoded data, you can even take this a bit further, right? Because if I have this dictionary encoded value here, 1, 1, and I see that it's happening 3 times in a row, I only have to run the function for element 1, 1, as opposed to having to do it for anything else. So that is going to be a very nice optimization right there. All right, let's go ahead and get into this conclusion, because my stomach is going to fall apart fairly soon. Basically, one thing that Presto aims to do, or Trino aims to do really well, is to minimize tuning as much as possible and just be adaptable. So again, you have all of these outcomes that you want, but ideally you build a system that can kind of take in current data and then adapt such that you're getting the performance that you want. So one really good example of that would be this multi-level feedback queue, where on every single node, the queries that should be running quickly are running quickly, and the ones that aren't latency sensitive are not, and you're still getting a ton of really good CPU usage. Of course, like all of the other papers that we've read, they all care about getting a lot of metrics, right? So write a bunch of counters, get a bunch of logs, figure out what's going on, because that's going to allow you to optimize it based on what's actually slow. Another thing, and this is kind of an interesting one, is they prefer static configuration over dynamic configuration. So what that means is you have all these settings to actually tune the system, and it's a whole lot better if those are static and stay that way for the entirety of the time Presto or Trino is up, because it's harder to reason about when someone can change them in real time while the system is actually running. And then finally, they do mention that it can be worth the investment to occasionally write your own libraries, even for these like kind of complex ones. So for example, I think they wrote their own compression standard as well, and they did find that it ultimately gave them a lot of performance benefits. Obviously, you have to be, you have to have a lot of developer resourcing for this, and it has to be worth the trade-off, but they do mention that sometimes it can be. Anyways, guys, I hope you enjoyed the video. It turned out to be a little bit longer than I was expecting, but not complaining because I think it's an interesting topic, and I hope you guys have a nice day.